Let's talk about large deviations, since this is one of the major areas in your early work, and you did some incredible work there. So you started the work after the student of Monet his work, and then did Moni join in? Because you have lots of work.
Not at that time. I mean, this was, 64 and 65, I worked on large deviations. And there was a joint seminar between Rockefeller University, I think at that time it was called Rockefeller Institute, and New York University Courant Institute, which I think in the fall it used to be there, and in the spring it used to be here. And Mark Katz was running it there, and then we'd go there and come back. Once I was coming back with a group of us who went there in a taxi, and somebody mentioned something that somebody had done, that if you take a Brownian path and if you look at the ratio of the two fundamental solutions, one with free whole space and one directly bounded data for a domain, the ratio sometimes goes to 0, sometimes goes to 1. And for the ratio to go to 1, for all points in the domain need to be convex.
Mm-hmm.
The idea for that is that directly boundary condition means not exiting the domain, and Brownian motion in a very small time will go in a straight line. So what that means, between any 2 points, the straight line must be contained in the region, which gives you convexity. So that's the idea behind the proof. So when I heard it, I said, okay, what would happen if it was not a flat space?
Mm-hmm.
Okay, then if a diffusion went from point A to point B, then it should go along the geodesic.
Right.
Okay, turned out that was in fact a large deviation result, and I thought that should come from an asymptotic formula for small time for the fundamental solution, just like heat equation as u to the minus, whatever the exponent is, there should be a similar exponent. I asked Louis and the PDE people, they gave me various estimates, nothing was precisely that. So I was able to prove it, and then use that to prove the required large deviation principles and so on.
So you did this work, but still this does not illustrate to me when you started working with Moni and Dan Strock on this.
Well, this was still in 64 or 65 when I was still a visiting member. And I think essentially it was this work with PDE that sort of people liked at Courant and offered me a regular position. So I joined the faculty in 66. And just before that time, I had met Dan Strock at Rockefeller, and he was very much interested in what I had done, and we started talking, and then we thought that some of the properties that we used could be useful in characterizing diffusions.
Mm-hmm.
So we started looking at how best to describe a diffusion process, and we developed what we call martingale approach to diffusion problems. And this was something that Dan and I worked on essentially from 66 till about 72. And that was an important work because it sort of makes possible to define diffusion process. At least the definition is possible without using PDE. Then it's possible to define it in infinite dimensional spaces or other settings where PDE theory doesn't really exist.
Right.
Although PDE needs to come in if you want to prove certain properties of this or certain uniqueness properties and so on, there are various methods of proving it, and PDE is one of it. And what it does, it unifies various possible approaches.
So you did this work with
Dan
and
that was a whole series of related things, and this means you have new methods for proving limit theorems, and a similar thing with boundary and without boundary, and so there was a lot of related work that went on for a period of about 6 years. And then Dan left to go to Colorado, and I took a sabbatical. And I was in India because I had at that point 2 boys, and you know, it was time to visit grandparents in India. So I spent a sabbatical year. Half of it I was in Sweden for half, and then in India for the other half. I came back in fall of '73. That's when I started working with Donsker on large deviations again.
Did you try to use this work on diffusion to do something in topology or geometry, because it was quite fashionable to use diffusion, the heat kernel, to get topological information? And did you try to go into that direction? I'm
not at all. I think I'll tell you exactly why. Because I didn't have a formal education in mathematics. You know, my knowledge of topology and differential geometry and so on was absolutely zero. You know, so I concentrated more on the probabilistic and the statistical aspects rather than on the, you know, differential geometric or topological side.